So, okay, so redshift. Well, basically, let's just remind ourselves about what we said at the beginning, which was that redshift. So light color is basically our brain's representation of wavelength. We can detect light between this wavelength, 400 nanometers, and 700 nanometers. And the different wavelengths, our brain basically uses what we call color to see these different wavelengths. We did a video about cones and rods earlier on, about how the eye works, but for now we just think color means wavelength. And that visible part of the blue, green, yellow, orange, red, and so on, that's just a tiny part of the electromagnetic spectrum. Now, if you have an object that is emitting a wave, like a light wave, and that object is moving whilst it's emitting the wave, then the waves in front of it, as it's moving, are going to get squashed up. And the waves behind of it are going to get stretched out. Now, if you follow this, if you click on this PowerPoint and open it up, and you run it as a presentation, you'll be able to see how that happens a little bit more clearly. I don't want you to think about it as waves as being like a solid object. They are things that are emitted, but as the emitter of the wave is moving, it's a sort of catching up with the wave that it's emitted, and as a result, the wavelength gets shorter, as opposed to thinking that the wave's getting squashed up. But I mean, you won't really. You could probably get away with saying something like the waves get squashed up or stretched out. Now, if this is a light wave, then when we get a shorter wavelength, it's going to be more likely move towards the blue end of the spectrum, which means that we call it blue shifted, rather than if it was stretched out, it'd be moved towards the red end of the spectrum, and so we would call it red shifted. It doesn't mean that things that are red shifted are necessarily red. It just means they've moved towards the red end of the spectrum. So it could mean that something was yellow and now it's orange, or it's green and now it's yellow, or it's red and now it's actually not even visible anymore, but infrared. So remember that the rest of the waves are just like light waves. The only difference being is that we're not able to detect them. So blue shift is the opposite. If something's moving towards you, or you're moving towards it, in fact, then the light waves get squashed, and so it's shifted towards the blue end of the spectrum. So it turns out that most of the galaxies in the night sky are redshifted, which suggests that they must be moving away from us. And if they're moving away from us, then you rewind the clock, and they obviously used to be nearer to us in the past. And so that's why we believe that's one of the reasons why we believe in the Big Bang. One of the things that was noted, it's a bit harder to understand why, but for now, we'll just say this adds to the evidence of the Big Bang. The faster, I didn't explain, I missed a point out. So the other thing to note is that when something is moving more quickly, then the redshift or the blue shift is more exaggerated. So if something's moving away from us very quickly, it's going to have a greater redshift. It's going to be stretched more. That sort of stands to reason. We know that if something's moving away from us or towards us, it's going to be redshifted or blue shifted. So if it's moving away from us a lot or quickly, it's going to be redshifted a lot. So then it was noticed that not only are most things in the night sky moving away from us, or most galaxies in the night sky moving away from us, but also that things that are more distant are moving away from us more quickly than those that are closer to us. So things are pretty much all of them are moving away from us, but the ones that are far further away from us at the moment are moving away more quickly. Now that part is difficult to understand why that would be. Why is that evidence of the Big Bang Theory? But we could touch upon that later on. For now, those are the key points about redshift. We'll just quickly look at this here. Without going into too much detail, this is essentially like a fingerprint of a star. it's kind of we analyze the light emitted from a star, and we think, okay, so these black lines are actually the wavelengths that the star does not emit, okay, or possibly this light that it does emit. But in any case, we can think about it. This is like this pattern, sort of as a fingerprint, that tells us what kind of star we're looking at, and so that was how we were able to identify when the light was redshifted, because we saw this pattern shifted towards the red end of the spectrum, which meant that it suggested that all the wavelengths that it was previously emitting are now stretched, and vice versa. This would be blue shifted. So this is how it was discovered. I mean, how do we know when we look at something that's red? Might just be red, right? We don't know how. We can't just say, oh, it's red, therefore it's moving away from us. That's silly. There needs to be a stronger bit of evidence, and that's what this is all about here. This bit here we won't go into quite so much now, but yeah, that's the basic summary of redshift. The next thing to look at is this idea that if something is really redshifted, it's no longer even visible. It goes into the infrared and then into the microwaves or radio waves and so on. Okay.